Okay, now it's time for the second talk of this morning. As I mentioned with the first ones, the two speakers don't need any introductions. Peter is also an expert on integrable systems and definitely also on Painlev. He is very involved with me on the chapter on Painlev in the digital library. I hope to discuss more with him about that today. And he will talk about classical solutions of the fifth Painlev equation.
Thank you, Audrey, and thank you for the organisers the opportunity to speak at this workshop. This is joint work that starts with Claire Dunning, my colleague, and two graduate students, Sanjita Islam and Bryn Thomas. Bryn actually was a few years ago, and the problem's been taken up more recently. As Audrey said, I've been involved with writing the Painlev chapter of the digital library. And one of the things I found when starting to prepare that and to writing it is that many of the results were given there were not exactly in an accessible form that the digital library were really wanting, something that people could understand in rather more simple mathematical terms. And I also found there's a number of gaps of things, and some of the work I'm going to describe today comes out of some of that kind of work. I'm going to look at classical solutions of the fifth Painlev equation. Nalini introduced the Painlev equations, as we'll say more. So I'm going to look at this fifth one, but in two particular variants. The standard form, when you have generic form, when you have delta to be non-zero, and then the term when delta is 0, and you assume gamma to be non-zero. As you shall see, this is related to Painlev 3, but has an interesting property in its own right that you don't necessarily see just directly from looking at Painlev 3. And then I shall hope to have some time for some applications towards the end. So, there are the 6 Painlev equations, which many of you will know. These derived in the late 19th and early 20th century by Painlev, Gambia and their colleagues. And they involve arbitrary constants, alpha, beta, gamma, and delta, or certainly the second or the fifth are. Now, as Nalini mentioned, the general solution is transcendental. I'm actually interested in solutions that are not transcendental, the so-called classical solutions of them. And related to the Painlev equations are 6 second-order, second-degree differential equations, often called the Painlev sigma equations. There's a one-to-one correspondence between the solutions of the Painlev equations and the Painlev sigma equations. In some respects, the solutions of the Painlev sigma equations can be written in a rather simpler form. Certainly the special solutions can be, but they also arise in applications in a very number of ways. And I think that's one of the main reasons why there's an interest in trying to look at these as well. So, to summarize some properties, the general solutions are transcendental. The second to the sixth have these special function solutions expressed in terms of the classical special functions for certain values of the parameters, but they only depend on one arbitrary constant. Second to the sixth also have rational solutions which involve no arbitrary constants. There might be an arbitrary parameter, but there's no arbitrary constant in it. And they have algebraic solutions of P3, P5, and P6. And one of the things about these is that commonly these solutions can be written in terms of Wronskians and certainly in forms of determinants. They're not every of them all. There's still one or two that are missing where we don't know the determinant. And so that I'm going to say a classical solution of the Painlev equation is either a special function solution, a rational solution, an algebraic solution, or a solution in terms of elementary functions, such as gamma functions and exponentials. So now let me look at the fifth Painlev equation. In the generic case, I'm going to set delta to be -1/2, which I can do by rescaling the variables as necessary. So if it's non-zero, I can definitely scale it to be that. Now, special function solutions, these are known to be in terms of Kummer or Whittaker, or have geometric case, and arise in these cases for the parameters. So there's a classification of when these actually arise. And it's been known for quite a long time that you can write them in terms of a determinant. So it's a determinant where the differential operator is zd by dz, and these are in terms of Kummer functions. So we can actually get solutions in this particular way in terms of Kummer functions. So a well-known result. And you can get some of the others by just the Backlund transformations for the other choice of the parameters. On the other hand, rational solutions, these were classified in 1994 by Kitaev, Law, and MacLeod, and they come in 3 different forms. Together with those, you can get through these additional symmetries here. So you could put them in 5 forms, but you can actually just write them like this. So to write them in terms of these 3 particular forms. And I'm going to look at these in a little more detail now of what you can actually do with them. These involve a parameter mu and integers m and n. Now in the first case, I'm going to call these generalized Laguerre polynomials. These come from special cases of the special function solutions. It's because the Kummer function for certain choice of the parameters is just an associated Laguerre polynomial. And so I can write, I'm going to define a generalized Laguerre polynomial as being this determinant, in fact you can think of it as Wronskian, of Laguerre polynomials. Now you can get this from the special function solution just using properties of Laguerre polynomials. You can rewrite this polynomial Tmn in various different ways according to your just using properties of Laguerre polynomials. And then you take in a particular combination of them, you can get the rational solutions of Painlev 5. Now, so this is where this is going to work. So if we look at what we found was rather than look at the variable z to try and understand the structure of the polynomials, it was better to use the variable z squared. And what I'm going to do here is I've taken epsilon to be 1. I'm just going to vary mu. And what you see is you have a pattern for one value of mu, and then you can know exactly when they have multiple zeros at the origin. The origin is the only place where the polynomial can have multiple zeros. So it's the only place where you can have multiplicity, and you can work out exactly known to the discriminant, exactly for which values of mu it's going to be. It turns out to be certain negative integers for all of them. And here's another one where you can see how the shapes change, and they go from one, well, it's a rectangle in some form, but not quite a rectangle because the edges are deformed. Now what you can do is try, and if you study them in a little more detail, you can see that the roots of the polynomial come into certain regions, which I've shown by different colors, and these are for 2 specific values of mu. You can classify them, and you classify them using certain combinatorics and looking at the partition functions and looking at the quotients and the cores of what the partitions actually are. You can actually do a classification of them, and so you can see from here you get different kind of shapes involved, some triangular, some more rectangular, and then there's some trapezium in here as well. So you can get various different ones that you can have from here. So you can get different kinds of things. So you do this classification in terms of the parameter mu. It's much easier to see what they are using the variable z squared rather than z. There's also a non-uniqueness of the rational solutions. Now, in most cases, it's been thought that rational solutions of Painlev equations are unique. So for one value of the parameters, there is only one and only one rational solution. Well, this is not true for Painlev A5, and I've given some results here as to when you can actually get other ones. You actually have to take this parameter mu to be an integer, and then you can get some non-uniques of solutions. They gave the results, but it's easier and simpler to see that here's a specific example where I have got two rational solutions here, and they clearly are not the same rational solution. You can't go simply from one to the other, and yet they satisfy the same equation with the same parameters. So proof by existence that here is an example that they cannot be unique. This is a counterexample to show that they definitely are not unique. Now, this is going to be important in an application I have coming up later. It's what I realized that, as you'll see later, how it came up. Now, in the cases 2 and 3, these are in terms of generalized Umimura polynomials. Umimura wrote down some polynomials in 1996 related to the rational solution of Painlev A5, and they were subsequently generalized by Masuda, Ota, and Kajiwara, but they wrote in terms of this determinant, but this is not an easy determinant to actually evaluate, because you see that the p's are going down here, the m's are going, the q's are going up. So you've got them going in different directions, and they're not written as a Wronskian either, so you can't do as much from a point of view of partitions. They did write them as a couple of differential difference equations. So by using properties of Laguerre polynomials, I'm going to introduce the generalized Laguerre polynomial in a slightly different form, but now written as a Wronskian of two sequences of functions. One is a Laguerre polynomial, and the other is a Laguerre polynomial multiplied by an exponential, and then you have to, of course, multiply by the equivalent exponential to the entitled Wronskian, so you get a polynomial. Now these have degree a half mn plus 1, a half nn plus 1, and they have various symmetries involved in this parameter alpha. Now the definition here is just given for m and n both to be integers, positive integers. You can extend it to be negative integers using these relations here as well. The reason you actually know they're going to be negative integer solutions as well is because they satisfy coupled differential difference equations, and from these you can go along the whole for m and n to be integers, not just positive integers. You can actually go the whole way. So you can, and then just by looking at the symmetries of it, you can work out how you're going to get between the two lots. So you can actually work this all out. Okay. So here is the result of where they actually are as rational solutions of Painlev A5. They come in, this is cases 2 and 3, but case 2 has to fit into two cases depending on whether this is n plus m or n minus m. So you put in n to minus n basically, so you get different sets. And then you get another form given by here. So we can write them all explicitly in terms of these generalized Umimura polynomials. The benefit of writing them as these polynomials rather than the ones previously written is I have them as Wronskians, and I can now do some combinatorics on them. I'm not going to look at give you any detail, but just give you some information. So now, if you take the Umimura polynomial U54, and again I let z replaced by z squared, and then you see different triangles, and then they go in and out just in where the discriminant is 0, and the triangles come back again. Same for a different choice of the numbers, and these relate to where you can actually, what you start in and end points actually are in this sequence. But I think more intriguing is if you look at this classification, which was done using partition functions, looking at them in some detail. These are two specific generalized Umimura polynomials, and you can see here that you've got in the one on the left combination of triangles, and rectangles. These are not exact because the sides are shaped. But if you add this one as well, you've got a triangle here and you can have a trapezium there as well. It took quite a while to work out this classification because if you actually looked at lots of them, some of these appear and some don't as the different sectors. And it depends on the choice of the parameters to which ones appear when and where. But we have done a complete classification. That's in Sanjida's thesis. So I mentioned about the Painlev sigma equation. So for Painlev 5, this was written down by Okamoto and Jimbo and Miwa. And you can write the rational solutions in terms of the generalized Laguerre polynomial and the generalized Omimura polynomial. Now, one of the reasons I said these are somewhat simpler to write down is that now these only involve one of the polynomials, whereas I had to have 4 of the polynomials to write the solutions down for Painlev 5. So in some respect, this is why it's somewhat a simpler issue that they only have one of them involved. Okay, so now let me move on to the degenerate 5th Painlev equation. So now the term involving multiplied by delta is set to 0. I could set gamma to be 1 by rescaling z if necessary, but I'm actually going to leave it not going to normalize it like that. It makes it slightly simpler to describe it if I don't normalize it like that. I really just need it to be plus or minus 1, but I know that's only z to minus z, but it's somewhat simpler to keep it like this. So there is a relationship between degenerative Painlev 5 and Painlev 3 through the Painlev 3 Hamiltonian. So if this is the Hamiltonian for Painlev 3, all of the Painlev equations have a Hamiltonian. The one aspect about them is they're non-autonomous since they explicitly depend on the independent variable. And I put 2 parameters, a, b, and epsilon is plus or minus 1. And then you get a couple of system of equations for p and q. If you eliminate p, you get Painlev 3 for certain choice of the parameters. And eliminate q, you get this differential equation here. So if in this differential equation I make this change of variables, then I get to degenerate Painlev 5. Now this change of variables is something that's perfectly allowed in the classification of the Painlev equations. You're allowed a Mobius transformation, and here is the relevant Mobius transformation that you actually need to do. So this is how you get between Painlev 3 and Painlev 5. And so it's quite easy, and it's been well known for quite a time, that if you have a solution of Painlev 3, you get a solution of this degenerate Painlev 5 in this particular form, provided that the denominator is not 0. Now, in some respects, you can just leave it like that, and many people do. I personally think it's somewhat simpler to actually treat degenerate Painlev 5 as a separate equation as well. Just as when you're looking at Painlev 2 and you have the so-called Painlev 34, you can look at Painlev 34 in its own right itself without just simply saying it's related to Painlev 2. You don't need to go directly, you don't need to go through Painlev 2 to get the solutions. You can get them directly. And this is, I think, a simple way to do it, and how you can actually find out. So, first let me give you the classical solutions of Painlev 3. They have rational solutions where the parameters alpha 3 and beta 3 multiplied by an epsilon have to add up to 4n. And they're in terms of Omimura polynomials. Now, these are a slightly different Omimura polynomial to what it relates to Painlev 5. the same Umimura, it's just a different polynomial, and they're also in terms of the Gare polynomials. And it has special function solutions if the alpha and the beta add up to 4n plus 2, and they're expressed in terms of Bessel functions. Now, to discuss solutions of degenerate Painlev A5, it's convenient to make this transformation so I get this equation for u. So I'm just effectively changing the independent variable. It means I don't have as many square roots hanging around. And when you're doing calculations in Maple, it doesn't like square roots. So, well, for rational solutions, these were classified 20 years or so ago, and in fact, I wrote a paper in 2005 where I expressed them in terms of the Umimura polynomials. So you can actually get an explicit form in terms of the Umimura polynomials. I'm not having to go through Painlev A3, just purely using a direct definition here. So that is what the rational solutions are. They're well known. Now, special function solutions. Now, normally, when you get a special function solutions of a Painlev equation, you've got an associated Riccati equation of the form this here for some choice of f, g, and h. However, for the degenerate Painlev A5, there's no such equivalent Painlev. I can't just simply from here work out the second derivative and then replace the second derivative from the first derivative by what I have, and then I get a sequence of equations for f, g, and h. There's no solution of them. So there's no direct Riccati equation. I mean, for Painlev A3, a Riccati equation is given by this, which gives solution to Painlev A3 when alpha is kappa plus 1 and beta is minus kappa minus 1. And then you can, using that quantity, if you differentiate it, you add a multiple of it squared and a multiple of itself, you get Painlev A3. So you see there's a one-to-one correspondence between the solution, or there is a correspondence between the solution of the Riccati equation and the Painlev equation. You can't do that for degenerate Painlev A5. Now, Gromat, Lane, and Shimomura stated that it would have special function solutions just based on when you're going to have them for Painlev A3. That's not difficult to work actually out. You can actually have them. Now, what you can actually do is you can write the explicit special function solution in terms of this determinant, where you've got this operator x d by dx, where you then have the phi sub mu here is in terms of Bessel functions, and it depends on the Bessel function depending on the choice of epsilon, which is why I decided not to specify what the gamma was, because you get these different types of Bessel function in these different cases. So normally the first solution in the hierarchy, what we often call the seed solution, because then you use Backlund transformation to generate the hierarchy, satisfies a Riccati equation. But for degenerate Painlev A5, it doesn't satisfy a Riccati equation because we couldn't find one. However, what it does satisfy is a first order second degree differential equation. It's not difficult to actually verify this is actually the case. In fact, the self-same thing happens for P34. The first solution in its special function hierarchy, I don't think it's written down in the literature, does also satisfy a first order second degree equation. The second in the solution in the hierarchy is the first order fourth degree equation. And so it actually, the hierarchy is first order 2nth degrees. For Painlev A3, it's first order, and it's the odd degrees you can go up in the hierarchy of what the first order equation the solution in the hierarchy actually satisfies. So it's sort of like filling in the gaps. So here is your one that you have that. I mean, given that you have one arbitrary constant in here, you do expect, because it's the ratio of C1 to C2, that it's going to satisfy a first order differential equation. And so this is what the differential equation actually is. It's a first order second degree differential equation. So now let me look at some applications. The first one is related to CU random matrices. It involves a paper of one of the authors was Alexander. So in their study of joint moments of a characteristic polynomial of CUE random matrices, Bazar et al., and there's about 7 others I believe, including Alexander, were interested in solutions of this equation, which is the sigma equation for Painlev A5. N is the size, capital N is the size of the matrix, and K is an integer. And they obtained a solution, or they obtained this solution in terms of an associated Laguerre polynomial. Now you can generate this in terms of the generalized Laguerre polynomial, as you'll illustrate. So that was what their result was. So in terms of this generalized Laguerre polynomial, the rational solution can be written in actually 2 ways. It can be written as this function here, when epsilon equal to 1, or if epsilon equal to -1, this is what the solution is. And this is the same as what Bazar et al. Actually wrote down. It's an equivalent representation of it. Now these solutions are not the same. They're related by this transformation because the original equation is invariant of this transformation here. So what they found in they were looking at a solution of the initial value problem. And were you aware that it was more than one solution, Alexander? Well, but they do actually look quite different. Well, I've asked some of your other co-authors, and they didn't realize it was non-unique either. So if you take n equal to 2 and k equal to 2, here are the 2 solutions. Now if you just do an expansion about 0, then they only differ in the z to the 5th term. But if you do an expansion about infinity, then they're quite different. The coefficients that, apart from this term, is present in one and not in the other. So you definitely get 2 distinct solutions to the problem, to the initial value problem. I'm not sure how it affects the rest of the paper, but that's just an observation that you have a non-uniqueness for an initial value problem of a Painlev equation. Yes, the initial conditions they imposed. It's because the equation can actually have. You could think of it like that, yes. But I mean, you could be that given that for Painlev A5, without that, in the standard Painlev A5, I can still find non-uniqueness. Right. Right. Yes, that's unique. But I think it's because the equation is invariant under this transformation here. Yes, z equals 0. So therefore, no, I know, but it's just I'm trying to say that people can find non-unique solutions. It's not surprising about z equals 0, as you said, because it's a singularity. Yeah. But I think you just have to be slightly careful. That's all. but the point was just that you've got an initial value problem, you've got more than one solution. So you do have to somewhat be careful how you're going to try to use it. And the linear is right. Z equals 0 is a fixed singularity, so you would expect strange things to potentially happen about it. You still have to be careful. In fact, you're almost told to be careful because it's a singularity. Okay. So now let's look at some complex sine-Gordon equations. So here is a complex sine-Gordon equation, also known as the Paulin-Regular equation. If you look for a separable solution, you get this kind of second-order equation, which arises in other contexts as well. It's not one of those on Painlev's list, but you can turn it into Painlev 5 with gamma equals 0 using this transformation. You can also turn it into degenerate Painlev 5 using this transformation, but that's not one of the ones allowed in the classification, but it's still, from a point of view of trying to get solutions, is certainly valid as far as I've turned it into an equation I can get before. So now this is a case of degenerate Painlev 5. And from there, we also know that it satisfies these differential difference equations for which you get discrete Painlev 2 out by elimination of the derivative. You can also get the differential equation by eliminating the difference as well. Now, if you just look at equations 3, when n equals 1, they have these solutions in terms of Bessel functions. And then you can iterate and get all the other ones if you wanted to. Now, for bounded solutions, you've got to take only the Bessel I function, the modified Bessel I function, and then you can write the solution here for all n. You don't have to use the discrete here, just in terms of this Wronskian, or this determinant tau n, so that gives you the solution of this, this problem, directly in terms of modified Bessel functions. There's another complex sine-Gordon equation involving now a quintic nonlinear term, and it's associated with this, and it's equivalent to this Lund-Regge model here by making this kind of transformation. I'm interested in solutions of this equation associated with that Lagrangian. Now, if I look for a separable solution in this particular form, so it's just a separable solution. I've just used an Sn, the square root of Sn, because it makes a neater differential equation. And then from here, you can get it into Painlev 5 using this transformation here. Now, the transformation, you move z to 2i r, so you might think you're going to introduce complex numbers into the solution. Well, it just so happens that because of the parameters here, it doesn't happen. So you can actually get solutions in terms of generalized Omimura polynomials in this particular case. So it's case 2 with m and n, epsilon equal to -1 and mu equal to -n. And so you can actually write down the general solution for this in terms of, well, I've rewritten the general Omimura polynomial now in terms of Laguerre polynomials involving an IR, and this is what the solution Q is of in terms of this polynomial here to actually get that. Now, a number of years ago, there had been written a way of actually getting these solutions, but you had to do 4 Schlesinger maps to obtain Sn plus 1 from Sn. So trying to work up the hierarchy like this was going to take a long time, whereas now I can go all the way just in one go. Now, here are the first few vortex solutions, so you can actually go and work them out, but even you see by the third one, they're getting to be rather big polynomials. But this way, I've been using these generalized Omimura polynomials, I've been able to write down the solutions in a rather neat way. And the final example I want to do concerns generalized Charlier polynomials. These are polynomials with regard to this weight here. It's a generalization of the standard Charlier polynomial. And it was written by Schmidt and Van Eyck in 2012 that the recurrence coefficients in the three-term recurrence relation related to these generalized Charlier polynomials satisfy this discrete equation here, a discrete system, and they have the initial conditions in terms of a modified Bessel function. So, because there's a parameter t involved, the discrete equation, the recurrence coefficients satisfy not only the discrete equation, but also the total system. That's a well-known result. Now, if you let xn be an squared and bn be equal to yn, then this is what you get. And now, if you eliminate xn plus 1 and yn plus 1, you just simply get a system, differential system, involving xn and yn. And then from here, which I've written down here, so you can solve the first one for yn, substitute in, and you get an equation for xn. And that's a very similar to one we've already had. In fact, I can make this transformation, which is essentially what I did before, and get myself down to the degenerate Painlev A5. So you can actually then get the solutions. Now, if you solve for xn, this is what you get, where xn squared is this quantity here, and then yn satisfies second order, second degree differential equation. This is what it actually is. And making this transformation here, it comes down to this second degree differential equation that first derived by Chauzy in 1909. It also appears in the work of Cosgroves and Skoufis in 1993, and in Cosgrove's paper in 2006, where he showed it was solved in terms of solutions of Painlev A3. And these are what the coefficients actually are. If you write, so you've got the three-term recurrence relation related to the generalized Charlier polynomials, then the recurrence relations can be written in terms of this determinant here, delta n, where this coefficient in the mu naught is just the modified Bessel function. So you can actually write that down explicitly. And thank you for your attention.
Thank you, Peter, for this very interesting talk, especially by including the applications in the end. Are there any questions or remarks? No question. So I have a question, and that is, I remember from Frank Golver talking about linear special functions. He was always, for linear special functions, you always have a general theory, but you always have exceptional cases. And he was always saying, but in practice, we always encounter the special cases. Is there anything true here as well, that in practice, we often encounter these special function solutions if people encounter?
I think that the degenerate Painlev A5 does arise in a number of places, but people just simply said it's Painlev A3 in disguise because of this transformation. But the transformation does involve the square of Painlev A3 and its derivative. So it's a non-trivial, if you take the solution to get from one to the other, it's non-trivial. This is a much simpler way of actually getting those cases. But yes, it does arise in certain aspects.
Any other questions? If not, then let's thank Peter again. And it's time for the coffee break.